Forces and Motion. Section 2. Gravity and Motion. Key concept. Gravity can be an unbalanced force that causes predictable changes in motion. Suppose that you dropped a baseball and a marble at the same time. Which do you think would land on the ground first? In ancient Greece, around 400 BCE, a philosopher named Aristotle thought that the rate at which an object falls depends on the object's mass. If you asked Aristotle whether the baseball or the marble would land first, he would have said the baseball. But Aristotle never tried dropping objects that have different masses to test his idea about falling objects. Gravity and falling objects. Late in the 16th century, Galileo Galilei, an Italian scientist, questioned Aristotle's idea about falling objects. Galileo argued that the mass of an object does not affect the time the object takes to fall to the ground, as shown in Figure 1. According to one story, Galileo proved his argument by dropping two metal balls of very different masses from the top of the Leaning Tower of Pisa in Italy. The people watching from the ground below were amazed to see the two balls land at the same time. Whether or not this story is true, Galileo's work changed people's understanding of gravity and falling objects. Gravity and acceleration. Objects fall to the ground at the same rate because the acceleration due to gravity is the same for all objects near Earth's surface. Why is this true? Acceleration depends on both force and mass. A heavier object experiences a greater gravitational force than a lighter object does. But a heavier object is also harder to accelerate because it has more mass. The extra mass of the heavy object exactly makes up for the additional gravitational force. Acceleration and changes in velocity. Acceleration is the rate at which velocity changes over time. An object accelerates when the forces on it are unbalanced. Gravity exerts a downward, unbalanced force on falling objects. So, the objects accelerate. Falling objects accelerate toward Earth at a rate of 9.8 meters per second. So, for every second that something falls, its downward velocity increases by 9.8 meters per second, as shown in Figure 2. You can calculate the change in velocity, or delta V, of a falling object by using the following equation. Delta V equals G times T. In this equation, G is the acceleration due to gravity, and T is the time the object falls in seconds. The change in velocity is the difference between the final velocity and the starting velocity. If the object starts at rest, this equation gives you the object's velocity after falling for a certain amount of time. Air resistance and falling objects. Try dropping two sheets of paper, one crumpled in a tight ball and the other kept flat. What happened? Does this simple experiment seem to contradict what you just learned about falling objects? The flat paper falls more slowly than the crumpled paper because of air resistance. Air resistance is the force that opposes the motion of objects through air. The magnitude of air resistance acting on an object depends on the size, shape, and speed of the object. Air resistance affects the flat sheet of paper more than the crumpled one. The larger surface area of the flat sheet causes the flat sheet to encounter more air as it falls. Thus, there is more air resistance. Figure 3 shows the effect of air resistance on a falling object. Acceleration and terminal velocity. As the speed of a falling object increases, air resistance increases. the upward force of air resistance continues to increase until it is equal to the downward force of gravity. At this point, the net force is 0 newtons, and the object stops accelerating. The object then falls at a constant velocity called the terminal velocity. Terminal velocity can be a good thing. Every year, cars, buildings, and vegetation are severely damaged in hailstorms. The terminal velocity of hailstones is between 5 and 40 meters per second, depending on their size. If there were no air resistance, hailstones would hit the ground at velocities near 350 meters per second. Free fall and air resistance. Skydivers are often described as being in free fall before they open their parachutes. But this description is not correct. A skydiver is falling through air. As a result, air resistance is always acting on the skydiver. Something is in free fall only if gravity is pulling it down and no other forces are acting on it. Because air resistance is a force, free fall can happen only where there is no air. For example, there is no air in outer space or in a vacuum. The term vacuum is used to describe a place in which there is no matter. Vacuum chambers are special containers from which air can be removed to make a vacuum. Figure 4 shows two objects falling in a vacuum chamber. Because there is no air resistance in a vacuum, the two objects are in free fall. Projectile motion and gravity. The movement of a hopping grasshopper is an example of projectile motion. Projectile motion is the curved path an object follows when it is thrown or propelled near the surface of Earth. Projectile motion is made of two different motions or movements, horizontal movement and vertical movement. These two movements are separate, so they have no effect on each other. But when these two movements are put together, they form a curved path, as shown in Figure 5. Projectile motion can be seen in the following situations: a frog leaping, water spraying from a hose, a swimmer diving into water, balls being juggled. Horizontal movement. When you throw a ball to a friend, your hand applies a force to the ball that makes the ball begin to move forward. This force gives the ball its horizontal movement, which is movement parallel to the ground. After the ball leaves your hand, no horizontal forces are acting on the ball, ignoring air resistance. Even gravity does not affect the horizontal movement of projectile motion. So, there are no forces to change the ball's horizontal velocity. Thus, the horizontal velocity of the ball remains the same after the ball leaves your hand, as shown in Figure 5. Vertical movement. Gravity pulls everything on Earth down toward the center of Earth. A ball in your hand doesn't fall down because your hand is holding the ball. After you throw the ball, gravity pulls the ball down. Gravity gives the ball vertical movement, which is movement perpendicular to the ground. Gravity pulls the ball in projectile motion down at an acceleration of 9.8 meters per second squared, if air resistance is ignored. This rate is the same for all falling objects on Earth. Figure 6 shows that the downward acceleration of a thrown ball and a falling ball are the same. Because objects in projectile motion accelerate down, you always have to aim above a target if you want to hit it with a thrown or propelled object. For this reason, when you aim an arrow directly at a round bullseye, your arrow hits the bottom of the circle rather than the middle of the circle. Orbiting and gravity. An object is orbiting when it is moving around another object in space. A spacecraft orbiting Earth is moving forward, but the spacecraft is also in free fall toward Earth. Figure 7 shows how these two movements come together to form an orbit. The two movements that come together to form an orbit are similar to the horizontal and vertical movements in projectile motion. In fact, you can think of something in orbit as being in projectile motion but never reaching the ground. Orbiting and centripetal force. Besides spacecraft, many other things in the universe are in orbit. The moon orbits Earth. Earth and the other planets orbit the sun. Also, many stars orbit large masses in the center of galaxies. The path of an orbiting object is not quite a circle. Instead, the path is an ellipse. Anything in orbit is always changing direction. An unbalanced force is needed to change the movement of an object. So, there must be an unbalanced force acting on anything in orbit. This unbalanced force that makes things move in an elliptical path or in a circular path is called a centripetal force. The word centripetal means toward the center. Gravity provides the centripetal force that keeps things in orbit, as shown in Figure 8. Gravity and the solar system. Gravity plays an important role in maintaining the shape of the solar system. Gravity between the sun and the planets keeps the planets in orbit around the sun. Gravity provides a centripetal force on the planets. Also, gravity between a planet and its moons keeps the moons in orbit around the planet. Gravity also keeps asteroids in orbit around the sun. And gravity between comets and the sun makes the comets orbit the sun in very long ellipses. Gravity can also change the movement of very small things in the solar system. For example, the rings of Saturn are made of tiny pieces of ice and dust. These pieces of ice and dust stay around the planet in a ring because of gravity.